In this work, we present EmoSpaceTime, a dual transformer-based autoencoder for disentangling emotion and speech content in facial animation sequences. Many of the available methods for data-driven speech animation facilitating explicit emotion control are deterministic since they include the control signal on the input side in the form of one-hot vectors. As a result, the synthesized animation lacks dynamic emotional expression, as it fails to encapsulate changes in intensity over time and across subjects. In response, we leverage representation learning with a transformer to capture the nuanced variations in emotional expression more comprehensively. Using the contrastive loss, our model learns two separate latent spaces for encoding emotion and content-related facial motion patterns. To process animation sequences of arbitrary length, we use a transformer-based autoencoder. The model consists of two separate encoders, which process the same facial animation sequence during training. Instead of processing the animation control sequences directly, we learn the disentanglement in the frequency domain. This enables our model to better learn translation invariant features since frequency information is comparably stable under translations in time. To obtain a fixed-length latent representation that is independent of the input sequence length, we utilize learnable tokens for the latent variable. We concatenate the two latent codes and pass them to a joint decoder, which reconstructs the input sequence. To achieve disentangled content and emotion in facial animation sequences, we additionally regularize the latent codes using the contrastive loss. It ensures that emotion or content representations are close together when they correspond to the same emotion or speech content in the input sequence. Lastly, we use adversarial training to avoid blurred reconstructions. During inference, we can perform emotion swapping by encoding two sequences and exchanging the emotion latents between the two before decoding. In the following, we show the results from emotion swapping for three different emotions.
I told you, I happened to be at a more important meeting at that time. Honey, the cottages harmonize well with the landscape. That tourist resort is worth traveling to. I told you, I happened to be at a more important meeting at that time.
I think so. Maybe that's why it's cheap here.
I told you, I happened to be at a more important meeting at that time.
You're kidding! We'll never make it across in one piece. Let's cross out the light.
I told you, I happened to be at a more important meeting at that time.
Our method is topology independent and can be easily applied to any character that is rigged according to the ARKit blend shape model.
What do you mean, Mr. Smith? You said to make it brief.
Additionally, it can identify subject-dependent differences in emotion.
I told you, I happened to be at a more important.
The results indicate that the visual representation of an emotion is consistent per participant. Furthermore, it captures the temporal dynamics of the emotion source sequence. Compared to approaches leveraging fixed emotion labels, the results are a lot more vibrant.
The curtain rose and the show was on. The curtain rose and the show was on. The curtain rose and the show was on.
The neural decoding preserves correct vicemes.
The curtain rose and the show was on.
the learned emotion latent space is geometrically meaningful. As such, we can modify the intensity of an emotion.
The quick brown fox jumps over the lazy dog. The quick brown fox jumps over the lazy dog. The quick brown fox jumps over the lazy dog. I got away with wearing socks and hid the lack of civilization in high boots. I got away with wearing socks and hid the lack of civilization in high boots. I got away with wearing socks and hid the lack of civilization in high boots.
We can also interpolate between two emotion representations.
Hike the steep peak with a joyful heart and reach the summit.
Our contributions involve a dual transformer AE for disentangled representation learning of emotion and content in facial animation sequences, an extensive analysis of the facial emotion space through emotion swapping, as well as precise artistic control of emotion type and intensity through a geometrically meaningful latent space. Thank you for listening.